Well, I'm sorry? Welcome back. Is there an echo in here? I'm talking to myself. Try it now? Okay. Yeah, I'm hearing some kind of reverberation. Maybe, yeah, hit the door. That's better. That's a little better. Okay. So I started talking and said, yes, was someone talking to me? I'm talking to myself. Oh, it's that. Yes, something. Okay. No, I still hear the echo.
I wonder where it's coming from.
I don't know. I could just keep going, but.
Did you check all your audio knobs?
Try it now? Okay. Yeah. Is it? That sounds better. That sounds normal.
You're just hearing it coming out of the...
Probably out of the control room, yeah. For some reason it was particularly loud this morning. Okay.
Turned up and down.
All right.
Sorry about that.
That's okay. So you could trim off the first part of this video. All right. Well, welcome back, everyone. So today I'm going to talk about... I'm going to start chapter 5. Before I do that, I could ask, of course, the project is due today. Are there any questions on the project that I can answer easily up here? Yeah.
For the second part of the project, it is set like L transpose / P.
Right.
Basically, like when we solved L / P for the first part, there are two conditions which were specified. The first condition is like checking the parent of j equal to j plus 1.
Right.
And the second condition is non-zero. Whether the non-zero of
yes.
particular j is like having the difference of 1.
Right.
As per the project script, project4.m, we were specified like we were given the same L. We were not given the L transpose. When we were invoking our project file, we were given the same L. So
you're supposed to solve L. You're given L, but you're supposed to solve L transpose.
So is it like we are given the L and we have to look at? We have to perceive it the transpose way.
Well, yeah. I mean, just like CSLT solve. Okay, CSLT solve does not form the transpose. It takes in L, but it solves L transpose x equals 0. Okay, so what you have to think of is really what you have is an upper triangular matrix. Let's call it U.
It can be solved if there is only one the two conditions which I specified. Like one is like parent of j equal to j plus 1. That can be done in constant time. But to compute like that, to combine the to do a combination, we have to find the number of non-zeros between the columns. In that case, like we'll be going to each and every column and find out the.
No. You mean for the transpose solve?
Yeah.
Okay. Now let me explain then what's going on here. For the transpose solve, it's the same condition. You don't have to go looking. It's still constant time work. You have to go looking for non-zeros. If you do that, you're off base, because you can't think of this matrix stored by column. It's not. It's stored by row. This is just just look at it on its head. This is L. That's L. It just looked at it differently. And so in the L transpose x equals b solve, you're going backwards first of all.
Yes.
It's a you start here and work backwards. And just a minute. And then if you come across a column J, you have to look up and ask, is J minus 1, am I the parent of J minus 1? And if I have, say, if J minus 1 has 5 non-zeros, and I have 4, then J minus 1 is my child. And then I can lump the work for this together into a single triangular solve, into a single step. So I can only have to look at the row indices of my child to do that solve. So it's still constant time check.
So is it like non-zeros have to be looked upon this way, not this way?
Well, it's the same data structure. You're looking at the same thing. I mean, this is your data structure. It doesn't matter which way you look at it. The data structure, it's either L stored by column or L transpose stored by row. It's the same data structure. Right? L stored by column and L transpose stored by row is the same thing. The same data structure.
So
if I gave you this compressed column matrix and I said this is an upper triangular matrix stored by row, you couldn't tell the difference between that and a lower triangular matrix stored by column. You can't tell the difference. It looks just the same data structure. So just your viewpoint.
So to confirm the point, is it like from the L/B and L transpose /B in the project as we get the input, the way we look at the non-zeros is going to remain the same?
The way you look at the non-zeros. Well, your algorithm, of course, is different. You know, I don't know. But this is the data structure you have. You've been essentially think of if this is confusing. If this is confusing, think of L transpose X equals B and L is stored by column. Then just think of this. I have a matrix U and it's stored by row, and we're done. You know, and then I'm doing an upper triangular solve of a matrix that's stored as a compressed sparse column, sparse row matrix. That's all. It's and then so you get an index there, and you know it's different. I mean, if we look at you have to treat it differently, obviously, because if you look at let's see if I can pull up the chapter 2 notes. Whoops.
In the second case, we would explicitly have to find out the number of non-zeros in each row?
Well, you have it. You don't need to find the number of non-zeros in each row. You have it already. In constant time. If you start looking for non-zeros and counting them, you're doing the wrong thing. You have the number 5 instantaneously. This number 5 is the same as the number of non-zeros in the column j minus 1. It's the same thing. It's just the difference in the column pointers. Now they're row pointers. This is, like I said, it helps to be dyslexic. Yeah.
I'm sorry to ask this again. In the first part, we will be solving for x1. I mean the value. I mean the top left diagonal is like diagonal value is x1.
Oh wait, this is I've written up here L transpose X equals B, but yeah, if you want to make this LX equals B and go the opposite direction, yes.
Yeah. In the first part, we will be solving for x1.
And then x2.
And we'll substitute that x1 to the second row, and then calculate the x2 when we solve the linear system of equations.
Okay. Well, you all forgot something though. You forgot the rest of these entries as well.
Yeah.
Yes.
Yeah. First we solve for x1.
First solve for x1 and then remove x. Essentially, subtract these from the right-hand side.
No, when we do the combine, we will be like.
And then combine. They're just lumped together, right?
Yeah. So when we do the same set of linear equations this way, it seems like the x1 x5 unknown variable, which is in the top right corner, happens to be in the last column.
It's still x2 and x1.
No, x5, if x5 is there, the top left.
If I'm sorry.
If x5 is in the top right corner.
xy.
x5.
Wait, what do you mean x here? No, that's not x. X doesn't. X is the vector here.
I mean, like yeah. If the L5, I mean the L55.
L55 will be right here.
Yeah, that means it will be here.
If this is L55, yes.
Yeah. According to that, the previous value will be the transpose there. I mean, like it will be in the top right.
Right here? No, it'll still be here. This is L55, and this is L55 transpose. The diagonal doesn't move. The transpose is made.
But the value before the diagonal actually.
Okay, this entry right here. This is L 5, 4. Yeah, that will be here. L 5 comma 4 or equivalently, transposed. Look at LT solved in the book and look at the derivation.
Honestly, I made a mistake actually with that value.
The way to think about this, I think, is to not try to think of it in terms of L transpose X equals B, but think of it as UX equals B, where U is stored by row. And then you're done. Then just do an upper triangular solve, and you just come to row by row. You're just working up row by row. That's what LT solve does in the book. Works from here up.
And regarding the first part implementation, when we were given two options, either to use a workspace or to do it directly.
Right. Either is fine. Whatever you feel like.
I tried when I tried the both ways, there is no significant speed difference, but for many of the matrices, I'm getting higher value if I try it with the workspace.
Higher value? What do you mean? What's a higher value?
Speed up my time.
Better, higher time or higher speed up?
It's taking more time.
Taking more time.
Not drastically, fractionally.
That's possible. Yeah, I didn't. Yeah.
But without the workspace, it's giving me lesser values.
Less runtime, you mean?
Yeah. Okay. But in the lecture, we actually spoke the other way around.
Well, I explained both in the lecture. I said you could use either approach, and if you pick the workspace method and you do everything right according to the project description, and you don't get a speed up, that's okay. It's an experiment, right? Will this? Maybe my suggestion of adding a workspace was not correct, or maybe you could have done it more efficiently. But my point. Let me finish my sentence. My point is that if you follow the project description, okay, which is to say that if I've got a supernode here, okay, a collection of columns with the same non-zero pattern, then you better not read the integers of these subsequent columns. Okay, number one, you can't read those integers. If you do, you're doing it wrong, regardless of performance. Okay, the project specification didn't say you must get X performance, okay, or Y or whatever. So you need to read these integers, not read these integers, and you need to read these integers once, not if you have 4 columns, not 4 times. Okay, so if you read this integer 4 times, as opposed to reading 4 integers over here, well, that's also wrong. You need to just read this integer once. So, that's the whole point, is to exploit the structure to avoid excessively pounding on memory. Okay. Now, it's possible in your implementation that you're reading this integer 4 times, and maybe that could be the cause of the slowdown. I don't know. I'd have to look at your code. But if you try to just read this integer, the point of having the workspace, it means that you only have to read this integer once. Do the gather into your workspace, do all the work, and then write it back. Well, I guess you'd read it. Essentially, you'd read it twice in that case. You read it on the gather, you do the work, and you read it again for the scatter. So, but I should say the bare minimum number of times, then, not just reading it. You're reading it. You're doing the gather and scatter for this integer twice. A gather and then a scatter. But if you do it 4 times, right, then all you're doing is you're not really exploiting anything. If you read and write this integer 4 times for every entry here in this row, once then that's not the right strategy. So if you do all these things, if you whether you use the workspace or not, the point is if you properly detect these supercolumns and properly read just these integers and only read these integers, a constant number of time, regardless of how big the supernode is, twice perhaps, if you need to gather and then gather into workspace and then scatter, then you're doing the right thing. And if you end up with code that's slower, well then that's fine. I mean, you at least have properly attempted the experiment to ask the question, if I do this right, will it lead to a performance improvement or not? We don't know, but you won't have the answer to that question if you read these integers too many times, or if this is clearly asymptotic, if this is clearly inefficient in the way if you're pounding on memory back and forth and back and forth and back and forth 4 times, for instance, instead of once, then it's clear that the algorithm is wrong. Okay, so be sure you don't have that. And the same thing goes on the upper triangular solve. If you have 2 rows that are supernodal with each other that have the same pattern, then you should only be reading the integers of the top row. Or actually, if you want to read the integers of the bottom row, that would be fine too, but then you'd have to treat the diagonal separate, the triangular part separately, which is possible. You can do that too. Because if you have 2 pairs, if you know they're identical, you looked at this entry and that entry, you know that this is already j minus 1, and this is j and this is j minus 1. So you could read the integers of this column, row, vector, whatever it is. And then you have j and j minus 1. That's also true over here. If you wanted to, you could write this so that you would, since you know that the pattern here and here are the same, and you know this is j plus 1, j plus 2, perhaps. Well, you know these 3 integers already. You just read them in, and you've already found out that this is j and j plus 1. Suppose you looked at this and you said, oh, they're the same. You looked at this pair and you said that's the same. You look at this pair and you realize that those 2 are the same. So there's 3 columns that are all the same. You've just read in 3 integers, and if you like, you could just read these integers next and use those instead of these, because you've got those 3 integers already and then this one. You know these are already algorithmically, you don't have to read them again. It's j plus 1, j plus 2. And then the rest of these would be the same. So if you want to read these or read those, it doesn't matter. Just don't read them both. So you could actually do it. I didn't mention this before because this is not, well, either. I mean, this is a trivial difference here but if you, the point is if you read both of them, of course, then it's wrong. But if you read one of them, I mean, if you just read this one, for instance, that's okay. I'm expecting to see lots of different approaches to the problem. That's the point. Because there's lots of ways of attacking this problem. And it'd be interesting to see who gets the best speed-ups. See which is the best approach. So does that make sense? Okay. I'll be posting the next project hopefully by this afternoon. Okay, QR factorization. This is fun. I spent, let's see, was this 2007? I think it was. I spent a summer working on a sparse multifrontal QR factorization, exploiting cache and all of that. This is about a year after I wrote the book, and that was a consulting project for the MathWorks. So now it's the Sparse QR at MATLAB, and so I had the privilege of working with them on that. That was a lot of fun. So QR factorization is fresh on my mind. I'm also right now have a project in which I'm looking at doing sparse QR factorization on the GPU, on a graphics processing unit. So the idea there, and it's very similar notions to what you're doing here. A GPU does not like irregular access of data and irregular computation. It likes to say, okay, I have a chunk, do it. I have a chunk of work, do it. Do big chunks of regular work. Well, that's what you have here. right? When we have this panel here, you've got a chunk of work that's very regular. And the GPU can exploit that. Now, for a triangular solve, it's rather difficult to exploit that on a GPU because, although it would be possible, because the memory traffic compared to the work is comparable. You're doing about as much memory traffic as you're doing work. And the GPU is bajillions of times faster. Bajillion, that's a word for many. Many times faster than the memory. Certainly the link to the CPU is extremely slow compared to the computation speed of the GPU. So for anything like this to work on a GPU, all of this data would have to reside on the global memory of the GPU itself. You couldn't afford to ship this across the CPU, do the triangular solve. It's like, here GPU, here's a sparse matrix, do the triangular solve for me, and ship it all the way across to the GPU just to do one triangular solve. That's ridiculous. The matrix would have to reside on the GPU to begin with, because the time it takes to ship that matrix over would by far dominate the computations. Anyway, so what we're doing is we're looking at QR factorization on the GPU, and there we're exploiting similar kinds of structure, though, but just that there's a lot more work to do in the factorization than there is in a triangular solve. So QR is real fresh on my mind right now as a result. QR factorization is a sort of the Swiss Army knife of factorizations. If you're stranded on a desert island and only had one matrix factorization to take with you, it would be the QR. Because you could solve linear systems with it. I mean, of course, you're on a desert island. You're not going to be solving linear systems. Okay. I guess you could. I mean, there is a lot of silicon on those desert islands, right? It's just rather amorphous. So it's sort of the Swiss Army knife of factorizations. It can do least squares problems. It can do linear systems of all kinds. It can do it's the best way of handling rank deficient problems. You can do what's called a complete orthogonal decomposition. We're using 2 QR factorizations on a rank deficient matrix. There's lots of things you can do with it. QR factorization is the lead-in to a singular value decomposition, which is the Swiss Army knife of the Swiss Army knife of factorizations. It can do anything on any matrix, and it reveals all sorts of things about the rank and the null space of a matrix, the condition number, the norm, everything about a matrix is revealed by the SVD, and the QR is the lead-in, the first thing you do to compute the SVD. So QR is pretty important. The reason, though, in the book I'm talking about it second, okay, there's a flow in the book, Cholesky, QR, and LU. That's not the way they were developed historically, but that's the way they developed thematically or theoretically. Cholesky is the basis for QR, QR is the basis for LU, theoretically. So let's look at QR. The thing about QR factorization is it doesn't, at least in my derivation, I don't have what I've done so far. I've based everything on block matrix multiply. So assuming you know how to multiply 2 block matrices together, okay, that's how we do the factorization. That's how we do a triangular solve. That's how we derive all these algorithms. That's not how I'm going to derive this one. Is there a way of writing this as a block matrix algorithm? Perhaps. I just haven't found it yet. There are some block matrix operations that you'll see that I think help to simplify the description of the QR factorization. And I'll use those. Anyway, so with QR factorization, what happens is you've got a matrix here that's possibly rectangular, m by n, and you want to factor this into an upper triangular matrix R, which is this all 0, and an m by m matrix Q, which has no specific structure to it. So you might wonder, well, what good does that do us, right? I mean, how if I were to solve this now a least squares problem, I'm trying to minimize the difference between ax minus b, trying trying to make this norm of this residual as small as possible. Well, how does that help you? Because maybe with LU factorization or Cholesky factorization, you break apart the matrix into two systems of equations, each of which are easy to solve. I mean, the lower triangular solve, just you know right away what the last unknown is. You just divide by the diagonal and you're done. And you've got that here with R, but Q, how does that help you with Q? This is not immediately obvious. Well, the important thing about Q is it's a matrix that's orthogonal, or all the columns are orthonormal. They're all at right angles to each other. And what that means is that Q, the transpose of Q, is its own inverse. So Q inverse is equal to Q transpose. That's powerful. Okay, because when you're solving a system of equations, you can solve it by multiplying by the inverse. Now, you never compute the inverse, but here we have it already without computing it. If we get Q that's orthogonal, we have the inverse easily. Okay, so Q, in a sense, is its own inverse. Well, the transpose is its inverse. And so if I have QR equals A, I can take... so what does this mean? Q inverse is Q transpose. That means several things. Q transpose, Q is identity. Multiply both these sides of this equation on the right by Q. You get Q transpose, you get times Q, and here you get Q inverse times Q, which is identity. So Q transpose, Q is identity. Identity Q transpose is also identity. And QR factorization, don't show this in the book, but the idea is, let's see if I can recreate this. If I want to minimize AX minus B, okay, then there's another minimize the 2 norm. Then there's another very important property of orthogonal matrices, which I'm just going to state. I'm not going to derive these things. I'm not going to state them. The other thing about an orthogonal matrix, if I take and find the 2 norm of a vector, right? That's just the square root of the sum of the squares of the entries. And if I multiply that by an orthogonal matrix, I don't change the 2 norm. In other words, the way to think about this, if X is a vector in n-dimensional space, okay, here's my arm as my vector. The only thing an orthogonal multiplication is doing is it's rotating this vector around. Right? It can change it. It can move this thing around like if it's a 3 vector. Suppose X is a vector of length with 3 entries. So it's in 3-dimensional space. Okay. So here's this X vector. An orthogonal multiplication can do nothing but move this vector around like this. It can't change the length of my arm. It doesn't change the length of the vector. And this is really useful because suppose this vector points off and it has both an x and a y and a z coordinate value. Well, what can happen is you can take an orthogonal, if you could camera down to the table a little bit, you can take this orthogonal matrix, you can figure out an orthogonal matrix so that when you hit this, when you multiply Q against this vector X, you slap it down on the table like this along, for instance, the x-axis, which sets the y and z component of this 3 by, of this vector in 3 space to 0. So you've zeroed out 2 entries of the vector. So you can choose Q. So I have a vector X with 3 non-zeros in it. I can find a Q very easily, actually, using several strategies, Householder and Gibbons rotations, such that it looks like this. I've introduced zeros. And the 2 norm of this doesn't change. Now, if the 2 norm of this doesn't change, well, the 2 norm of this vector is the square root of the sum of the squares. But there's only 1 non-zero in it. The rest is all 0. This must be, then, the 2 norm of X. Right? Because it's the only thing left. So if this is the length of my arm and I slap it down, then the length of that arm is the length of my arm. Right? It's the length of that vector. So orthogonal operations are useful. And if I'm trying to solve, this is called the least squares problem because you're trying to minimize the sum of the squares. The 2 norm is just the square root of the sum of the squares. If I want to find, if I have an overdetermined system of equations, I have A, X equals B. I have too many equations for too few unknowns. So I can't make AX equals B. I don't have enough freedom to do that. So I want to make A times X as close to B as possible. And so what does that mean? Well, one strategy is to say I want to I want to find an X that minimizes the sum of the squares of the differences. And so that's this problem statement here. Well, so now we have a 2 norm. We have a vector. This residual is a 2 norm. I mean, the residual is a vector, and I want to minimize the 2 norm of this residual. But multiplying by an orthogonal matrix doesn't change the 2 norm. So if I find a way to minimize this residual, and it turns out that, well, I'm minimizing the residual that's been moved around in a different direction, moving this around by an orthogonal operations doesn't change the 2 norm. So if I move it around and then minimize the thing that I moved around, then I've minimized the thing that I started with, which is AX minus B. So, in other words, suppose I have an orthogonal matrix. Well, this problem here then is the same as minimizing the 2 norm of Q transpose AX minus B. If Q is any orthogonal matrix, any old orthogonal matrix. Well, if I pick this orthogonal matrix Q such that Q times R equals A, then R equals Q transpose A. And if R equals Q transpose A, so if I've managed to find a Q that if I pound Q transpose to the left of A, I get an upper triangular matrix. Okay. Then R is Q transpose A. Q is orthogonal, so I can take what I've done here. Let me just pause a minute. I've taken QR equals A, and I've pre-multiplied by Q inverse on either side. So this cancels. I have R equals Q inverse times A. Oh, but wait. Q inverse is the transpose. Okay. So, look there. I've got a Q transpose A. Hey, good deal. So now now this becomes the same problem as minimizing Rx minus B. Minimize that. Now look at Rx minus B. R has a very specific structure. Let me call it R1 and 0. Let's see. So if I block this up into 2 blocks, this is of size n, and this is of size m minus n. Then, no, this is a block unit. So this is of size n by 1 equals B. This will be B1 and B2. Well, it's B1 and B2. Whoops. That's B prime. I'm sorry. I should have, because it's Q. B prime is Q transpose B, because obviously I have to multiply Q transpose times B as well. So now I'm trying to minimize this thing, and this thing has this vector Rx minus B prime has this structure right here. R has this upper triangular shape, and there's a bunch of zeros down here. So what do we have? We have R1. This breaks into 2 pieces. I have 2 pieces here. I've got this Rx minus B then I can write as 2 parts. I can write it as R1x minus B1 prime and 0 minus B2 prime. So that's my residual vector. It has the x's only affect the top part of this. They don't affect the bottom part. That's really useful. Why? Well, think what I'm trying to do. I'm trying to minimize the length of this residual vector. That's the goal. The length of this vector is the square root. Let's ignore the square root. Because if you minimize the something, and then you've also minimized the square root of that something. So let's forget the square root for the moment. I'm trying to minimize the sum of the squares of these entries of this vector. So what are the sum of the squares of this vector? It's this all these entries, take them and square them. Take the next entry, square it, and then sum it up. Well, I can slice this problem, that summation, into two parts. The sum of these squares plus the sum of those squares. And I want to find an x that makes that total summation as small as possible. But no matter what I pick for x, this part is not going to change. I have no freedom now to do anything at all to this part of the vector. So, darn. I can't make this any smaller than it is already. There it is. It's just there. No freedom to choose x. No matter what x I pick, this is not going to change. But what about this? Ooh. This is a square upper triangular system of equations. R1 times x equals my R1x. I mean, look at it now this way. I now have a piece of my equation. I want to make. So in other words, I can write that Rx minus b equals squared. So I'm throwing away the square root. R1x minus b1 prime plus this squared. So the sum of the squares of this is the sum of the squares for that plus the sum of the squares of that. Well, I want to minimize this. I want to pick the x that makes this as small as possible. Well, I can't pick an x to do anything to that, but I can pick an x to make that 0. I can choose Rx so that that's equal to 0, because this is a square, well-determined system of equations. It's n by n. Just solve R1x equals b. So I can pick the x that sets this thing to 0. And I can't pick any better x than that to make this residual as small as possible. If I make this residual as small as possible, then so I've made this as small as possible. Because I've chosen x to make this as small as possible, that's the same x that makes this as small as possible, because this is the same equation. And then if I make this as small as possible, well, then multiplying this residual vector times an orthogonal vector doesn't make it any different in length. It just flips it around. So if I make the length of this vector as small as possible, I make the length of that vector as small as possible, and that's my goal. Is to make the length of the residual vector here, ax minus b, as small as possible. So that's how you solve a least squares problem using QR factorization. So now that you see the big picture, and hopefully some of this is review. Hopefully you've seen some. Maybe you've seen some numerical methods before. You've seen. I mean, I know I teach this in my undergraduate numerical methods course. What you've just seen. I just wanted to bring it up, fresh in your memory. If you haven't seen it before, that's okay. You've now seen it. So this is the magic of QR factorization. It turns a least squares problem into a linear system, upper triangular linear system. We can then solve it really quickly. Okay, so then now the question is, well, how do you compute this? Lots of ways of computing it. And I picked one particular method for the book. Yeah?
I may be getting ahead of myself, but could the way you compute QR affect the ultimate 2-norm of your... If you could you compute QR so that your B matrix was top heavy or bottom heavy?
Okay, the question is, can you compute the QR such that the A or B is top heavy or bottom heavy? No.
Okay.
No. No matter. I mean, there can be different r's in different q's here. But let's see.
And to use your three-space example, I was thinking that you could come up with a Q that puts it on the x-axis, but you could also come up with one that puts it on the y
or
or
the
the
z, exactly.
So if your choice of Q can affect that, it would also affect your B.
It affects, well, here's the thing. It's this residual vector, r equals ax minus b. So if you need to answer this question, I think it's probably easiest to step back a bit and ask the question, what can I do to r? I think that's rather than trying to slice it apart, I do see your point. Looking at this, it's not clear, well, wait a minute, is there a different r, a different q that makes b2 smaller? Maybe. That's what you're asking. Because it's like breaking it into two parts. You've zeroed one part, but maybe there's a way of picking the q. I see your question. It's a good question. But I think the answer to that is to not get so detailed closely looking at this split of b into two parts, but just to look at this. Okay. We have this residual vector r that I'm trying to make as small as possible. Trying to find an x that makes this as small as possible. And whatever it is, however it is that I find that x, suppose I find the magic x that makes this as small as possible. Let's suppose that is unique. It wouldn't have to be unique. If the system is ranked efficient, there can be lots of answers. But let's suppose it's unique. So I have one residual vector. Well, if I take this and I multiply Q transpose times R, then yes, I could pick lots of Q transpose R's to move this Q transpose R in any which direction you like. You could move it on to the x-axis, to the y-axis, to the z, to the... Okay. But it's still going to be the same length. So you won't be able to make it any smaller. That's the, I mean, if you have found, I guess the point, stepping back a little bit, if I have made this as small as possible, if I've chosen an x to make r as small as possible, then any Q transpose r will be as small as possible. Because if I haven't, if I find another r that says, oh wait, this one's smaller, then I could take that and rotate it and I get a shorter r. So I must have an r that's as short as possible, and I must have, if I've picked an x to make r as short as possible, then it doesn't matter which direction it points. And since it doesn't matter which direction it points, it doesn't really matter what particular values you have down here. It's going to be the same length. This sum total length is going to be the same. So yeah, you do actually have freedom for what the values in here look like. There will be some differences. But the sum of the squares will be the same. If there is a unique solution. If there's not any unique solution, let's see what will happen. I guess there still is a unique shortest r. It just may be that different x's will give it to you. Right? There's going to be a smallest possible r. Across all possible choices of x. There's going to be a smallest, there might be more than one r that's smallest, but there's going to be a smallest r. And if there's a smallest r, then this approach will find it. Because I just minimized this. I made this as small as possible. This process here makes the residual as small as possible. Could it have been a different one? Yes, but it's still the same length. So yeah, that's a very good question. So now, what's the magic here? Well, the magic is to find, just as in LU or Cholesky factorization, we have these fundamental operators that we use to pound the matrix to zero things out. Okay. Well, I already wrote down that I can take a vector. I'll call it A now. Okay. And there are various methods, and I'm going to show you one, householder reflection, that it's called a reflection because it's like taking a mirror, and it takes the vector and it finds a mirror, and it moves the mirror along until it reflects this vector, not changing the length. It reflects it down along this mirror so that it's all along one axis. So the reflection here would be something like that. You have this mirror here you find, if you will, that if you look at it in the mirror, it's flipped down here, and this happens to be along, say, just the x-axis. So it's a three-dimensional vector, then all the other two components have been set to 0. So it turns out the way to, and I have, 4 minutes left, so I can't do that. Let's suppose we can find such a Q, such that Q times A, or I'm going to let me just call this H, because I'm going to switch to householder reflections really quickly. Okay, this is no joke. Now, if you square this, then that's a joke. Okay, a meta joke. I never met a joke I didn't like. So there's the H times A vector, and I can choose H, and I'll show you how to choose it, such that the structure of this vector looks like this. A1 prime, and then all this has been set to 0. So that's how you can. There's a method for finding such a matrix H, and there's an efficient representation for it. There's an efficient way to multiply this matrix times this vector that takes order n time, even though it's n by n matrices. This is an n by n matrix. And normally matrix vector multiply is n squared operations, but this is a very special matrix, and there's a particular way of doing it in a fast way because of its structure. It takes order n time. And it zeroes out, it can be chosen to zero out all but the first entry of a vector. And I'll show you how to compute H in a minute, or next class. But what we're going to do is I'm going to take my entire A matrix, and I'm going to slice it such that I have the first vector, I'll call it A1, and A2 through AN. So consider A as a collection of column vectors, and find a householder reflection which annihilates all but the first entry of A1. And how to do that I'll explain next class. So you can write this new matrix as a collection of columns H1A1, H1A2, H1A3, all the way down to H1A sub n. So you've got to multiply this householder all throughout everybody. And this work takes n squared time then, because if one of these takes n time, I've just done it n times. And now what does the resulting matrix look like? The resulting matrix has a first column which has been annihilated. So I have an entry here, and this is all 0, and then the rest of this matrix is all non-zero. Well, we're progressing, right? This is my goal over here, an upper triangular matrix. I'm moving towards upper triangularity. Now what I need to do is just take this vector on and below the diagonal and find another householder just for that. And so what I need to do is think of this matrix. Now I need to take this matrix and split it, because I don't want to touch this. If I modify this first column, if I just arbitrarily take this entire column and work on the entire column, then I'll rotate it. But in the process of rotating this column, I'll make this all non-zero again, because I've got two columns, and I just zeroed one of them out. If I rotate this other one so it's 0, then whoops, the other one's not all 0 now. It's off in three-dimensional space somewhere. So we have to be careful about how we zero out. We want to preserve these zeros. And I'm out of time, so I'll show you how to do that next. But the gist is that you want to leave this part alone and only work on this part of the matrix. So the top part of the matrix stays the same. This gets zeroed out to 0, and then you just repeat. That gets zeroed out. And when you're done, you've got an upper triangular matrix. And that's R. So I'll flesh out the details and look then at the sparse case on Monday. So see you then. Thank you.
Wouldn't that be